to the total right there. So I'm just taking this ratio, and by, again, law of large numbers and unbiased estimators, all that business, as n grows, this should converge to the probability of y sub j. Okay? So that's my proposition, that those proportions should converge to those probabilities. So with that, I could find the expected counts. But now I found the probabilities that I wanted. So now I'm going to tell you that to find the expected values in this two-way table is going to be this formula. The expected value of I comma j, whatever that I jth cell is going to be the row sum of the ith row times the column sum of the jth column divided by n. And the proof is right here. So right here, expectation is equal to the multinomial expectation. As we discussed right here, this probability is the same as just being in the intersection of those two levels. By independence, that's why this is in green. By independence, these split up. And for each of these probabilities, I'm going to use the unbiased estimator to replace them because I don't know what these are in the population. So therefore, I replace these with those estimates that I had in my proposition, and then I cross one of the ends out by algebra, and then I get this as my formula for expected values for any of the ijth cells in that table. Okay? You guys better hope on the final I don't ask you to explain this. Okay? Because again, we'll see, because I might be that spiteful. All right, so here's the expected value. So if you want to find the expected value of this cell, which whatever I and j are, it could work for any of these other ones, you just find the row sum to which this cell belongs, you find the column sum to which this cell belongs, you multiply those guys, and you just divide by the total number of observations in the table. Okay? That's how you find the expected value for every cell in the two-way table. Okay? So that's how you find expected counts. Again, I imagine your textbook, I didn't even look at your textbook for this section. I imagine they just tell you what the expected count formula is that you see on the screen, but I doubt that they tell you why this works or how to derive it. So again, you guys could be fine going the rest of your life not knowing it, but again, I don't imagine you guys figuring out why that formula is what it is on your own. Okay? So there it is. Once you find the expected value with their corresponding observed value, so notice I'm not saying that these are multiplied, I'm just saying that here's the observed value in this cell and this is the corresponding expected value. So once you find the expected value for all these cells, you just take those values, you subtract them, square, and divide by the expected value. Right here, this is the observed, this is the expected. Subtract them, square them, divide by the expected value. And then you do that across all of the cells until you get to the last one. Take that expected or observed value minus the expected value squared, divide by the expected value. Once you sum up all those terms, this just literally becomes this chi-square test statistic that we had before. Okay? And notice that again, the degrees of freedom are minus 1 times c minus 1. Okay? Okay. All right, so again, if you guys want to go to college and not pay attention, that's on you because you're paying thousands of dollars to be in the class. And if that's how you choose to be in the class, then I'm sure your parents would be very happy to know where their money is going and how it's being invested. Okay. Okay, so once you compute the test statistic, you get the p-value. Again, more reasons like this is the reason why I'm leaning toward not curving the final. So I know a lot of you guys aren't paying attention, so why should I do you guys any favors if you guys aren't willing to show any interest in your learning? Okay? All right, so p-value compared against alpha, and you make a decision. Once you get to that part, you've done all of what you needed to do for a problem like this, where you identify the procedure, chi-square test for independence, you state the hypotheses that we had in one of the very first slides, you check the conditions. Notice that we still have the large counts condition from Friday, where all the expected counts have to be greater than 5. Notice that independence is crossed out. Why don't we have to check independence? Yeah.
That's what we're testing for.
Because that's what we're testing for. That's what, under the null, we're assuming independence, so why do we have to check it if that's assumed to be true from the beginning? We don't have to check that condition for this type of problem. Here's our test statistic, compute the p-value, and then voila, here's your script, which is the same as it was before. Okay? All right, so again, that's your recipe, and do you guys have any questions about chi-square test for independence?
Is there an example for this?
There is. Okay. And again, a minute ago I was debating whether to stop teaching too. So again, you guys have to pay attention. It's incredibly disrespectful if you guys aren't keeping up. And if you're going to be so arrogant to say that you guys can learn this on your own without listening in class, be my guest, but I doubt you would be able to explain this to another person on your own. Okay? So, here's the example. At the 1% significance level, is there evidence to suggest that there's an association between a person's anger level and the risk of coronary heart disease? Okay, so in this problem, there's an observational study of a random sample of 8,474 people with normal blood pressure, and then after 4 years, because it's an observational study, they measured their anger level by some scale and checked their health with regards to their heart in terms of their risk of heart disease. And the information is summarized in the table right there. And it's our job right now to conduct a chi-square test of independence to test whether or not the variables anger level and their risk of heart disease is if they're associated. So notice that the language of the question is associated. So even though it's like, wait, aren't we supposed to do chi-square test for independence? Yes, but again, as I phrased in those slides, you could also use associated and not associated to describe the relationship between those variables. All right, so again, these problems, they don't require a whole lot of, deciphering. The information is all there in that table, we have everything we need. So this is one of those cases. This is unlike tests for proportions and means. You're actually, if you get a test or a FRQ like this on the AP test, they have to give you the data, where the data right here is summarized in a table. So for means and proportions, they don't normally do that, but for chi-square, they kind of have to. Okay, so just be aware of that. And then right here, we could get started. So obviously the first step is pretty straightforward. There's no parameters to identify. We just say what our objective is. So to test whether or not anger level, and heart disease risk are associated. An appropriate procedure is and then give me a moment to do this thing. chi-square test for independence with the following hypotheses. Okay, and then of course we just list them here. Oh, because I didn't do it correctly. Give me 1 moment. Okay, so under the null, the 2 categorical variables have to be independent. Remember, always phrase it in the context of the problem. So in this case, anger level and heart disease risk are independent. You could alternatively say, instead of independent, you could say that they are not associated. If you want to be more, again, using the same language as the question. And then under the alternative, anger level and heart disease risk are dependent. Dependent, which means that they're associated. So again, you could use any language you want. They mean the same thing. All right. So step 2, SRS. It says right there, they followed a random sample. So it stated that the sample of 8,474 people were randomly selected. The next one is large counts. Now, in this case, we have to find the expected counts, all right? So again, normally you would just have to say, okay, so for this cell right here, I would have to multiply this row sum, 190, with this column sum, 3,110, and then divide it by the n right there. You do this, again, across all cells. But luckily for us, a calculator will actually do that for us, all right? So if you guys have your calculators, go ahead and take them out. And then I will have to go back to the site for you guys to input the data, but it does have a slightly different procedure than goodness of fit, all right? Okay, so in your calculator, you guys have to put in a table. You cannot put in 2 lists and somehow the calculator is going to know to combine the list. No, you have to put the data in a list, or in a table, where a table takes the form on the calculator as a matrix. So if you look at the the 4th button on the left, you see X inverse, but at the top in blue you see matrix. You're going to have to press second matrix. And then I'm not sure if you guys have data in here. It doesn't matter if you do, we'll change it. But notice that I have some already here. I might actually change B really quick, but it's okay. Okay, so in order to input the data, you have to go to edit, and then you pick the matrix that you want to edit. In this case, you could just use A. Hopefully there's nothing there. You have to specify the dimensions of that table. So in this case, it's a 2x3 matrix, as we have 2 rows and 3 columns. And then you have these values to input. So let me go back to the original, and then you guys can input the data there, even though I just had it. But you can see that from the example, there's 2 rows, yes and no, 3 columns, low, moderate, high. So you have a 2x3 table, therefore input that in your matrix and then put the values in. So take a minute to do that, and then we'll move on to the next thing. Okay, so again, hopefully 6 numbers isn't too demanding from you guys. All right, so you guys have the data in your calculator. It's in a matrix 2x3, and then that's all you need to do. Just input the values in the table, and then you can go to stat and go to test and go to item C. Item C is our chi-square test. If you press enter, it's going to ask you for observed values, and it's in the form already as a matrix. And your expected values, which is in the form of a matrix, because again, if it's a 2 by 3 matrix of observed values, it's a 2 by 3 matrix of expected counts. Now, some of you guys are looking at, I don't have anything in matrix B. Why do I have to plug in anything for expected values when we didn't do anything with expected values? The reason for that is because whatever matrix you specify right here, the calculator is going to put in the expected counts in that matrix or they'll put it in automatically. So even though you don't have anything in B, or maybe you guys do, but you don't have to worry about it because the calculator will override it. Okay? So notice, and I'm just going to flip back to mine. Notice that my matrix B, I changed it to a 10 by 7 matrix, 10 rows, 7 columns. And notice that B was my expected counts matrix. But notice that the dimensions don't match up. It doesn't matter because, as I mentioned, you could use any matrix for the expected counts because it's just going to override it. So if I press calculate, okay, you're going to get this chi-square value, this p-value, and this degrees of freedom. All right? So hopefully you guys get the same thing. I'm going to write down the information right now before I leave this screen. So give me one moment. All right, so hopefully you guys have the same thing. Now, if you want to see your expected values, you go back to matrix and notice that my matrix B was originally 10 by 7. Now it's 2 by 3. Oh, because I wonder what must have replaced that matrix. And when you go here, those are your expected counts. The reason why you don't have to calculate them is because based on that formula, the expected counts are the row sums times the column sum divided by n. That's stuff that comes from the table, right? That's just a marginal distribution information. So when you put in the table, the calculator can compute the marginal distributions automatically, and it could do it obviously in one sweep as opposed to us having to do it 6 different calculations. So the expected values or expected counts are automatically computed when you use the chi-square function. All right? Any questions about that? Yes. It's if you go to test and you go to item C, it's chi-square test, and then observed is whatever matrix that has your data, and then expected could be literally any other matrix you want it to be, and then you just press calculate.
Like what's supposed to be in the matrix B?
Nothing. Or it could be literally anything because it'll override it. So my matrix B, I started off having a matrix that was 10 by 7, but then when I did the calculate, it turned into a 2 by 3 because it was overwritten to match the dimensions of my original observed matrix. Okay. All right. So again, it's working a little backwards, but it's fine because you're doing the chi-square test to get the expected counts. So again, you're kind of getting ahead of yourselves because we haven't even gone to step 3 yet, but we needed the expected counts to do the large counts condition. So that's why I have the stuff listed off to the left so I could have that for later. So below is the table of expected counts for each observed count. All right, and then because again, you can't just tell the AP reader, oh, trust me, I did it and I know that they're all greater than 5. No, you have to create a table of the expected counts to show them. So in this case, here's the expected counts. Okay, so I'm going to recreate the table, yes, no, and then low, moderate, high. And I'm just going to create a 2 by 3 table as the original table was. And then I'm going to physically write out the expected counts. I'm sure that because you didn't have to do each of the 6 calculations individually by yourselves manually, I imagine just copying down these expected counts should not be too demanding an ask. All right, so in this case, hopefully your expected counts line up with mine, but I'm gonna just write them out right now because that's what you're expected to do. Alright, so those are my expected counts from the calculator. You don't have to physically write out the formula. Pretty much I've seen that they just say just just show us the expected counts and then that's enough. So I doubt that they're gonna ask you to calculate individually all of them on the AP test. So once you show them the expected counts, you're gonna say, therefore, the large counts condition is satisfied because all expected counts are greater than 5, okay, which suggests that the sampling distribution is approximately chi-squared. Chi-square with 2 degrees of freedom. Okay, so notice that off to the left, from the calculator it says 2 degrees of freedom. Why is it 2 degrees of freedom? Well, if the number of rows I have is 2, number of columns I have is 3, degrees of freedom is equal to r minus 1 times c minus 1, which is the same as 2 minus 1, 3 minus 1, 1 times 2, 2. Okay, so that checks out. All right, so just the number of rows minus 1, number of columns minus 1, and multiply them together. Okay? So once we're done with the conditions, then we can move on to the calculations, where the calculations are pretty much done for us. All right, so I guess I'll just continue to write. The chi-square test statistic, chi-square with 2 degrees of freedom, is equal to the sum, I going from 1 to 2 because I have 2 rows, j going from 1 to 3 because I have 3 columns, so just be aware where these numbers are coming from. And then the test statistic, observed I comma j minus expected I comma j squared, divide by the expected I comma j. All right, and then my suggestion, as always, is just to plug in a few terms. Again, you're not manually calculating the chi-square test statistics, so the least you can do is just set it up and plug in a few values. So if we look at the first observed count, the first observed count is 53, so 53 minus its corresponding expected value, which is 69.731. Square that, divide by 69.731. The next one is 110 minus its expected count of 106.08 squared, divide by 106.08. And then at this point, I'm just going to do the dot, 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 and skip to the last one. I'm assuming that the reader could read or could fill in the rest of them, which is 606 minus 618.81 squared, divide by 618.81. Okay, so once you have a few of them plugged in, your chi-square test statistic is 16.0768. That came from the calculator with a p-value of 0.00032. Okay. All right, and then once you have the p-value, as you guys can tell, you're going to say that because it's less than the 1% significance level, we're going to reject the null. Okay, so formalizing that, that's where we're getting right now. Oops. Okay, so at the very bottom, because the p-value of 0.0032 is smaller than the 1% significance level, there is convincing statistical evidence that anger level and heart disease risks are associated. And that's all we have to say. Okay? So there is the whole thing. Not too bad, less writing than normal, but again, obviously the calculations look a little bit different because again, we're doing chi-square. Yeah.
My calculations are coming out wrong.
In that case, one of us has the data inputted wrong in the
I
calculator.
entered it wrong the first time, but then I fixed it, but my calculations are still coming out wrong.
It is right too.
Yeah, yours is right. I'm just having an issue. I
I
don't know.
don't know. The only thing that could cause the only thing that would have caused it if you didn't put the data in correctly. That's the only thing that
Double check it, okay? Alright.
can
I'll have to.
Elizabeth or SP double check it. Okay, because as of right now, I don't want to stop. Okay. Any questions about this example? Again, it's just your normal recipe for hypothesis testing, but again, it's just tweaked to do the chi-square test for independence. Okay. Any questions? All right. So, if there's no questions, then I do want to run through chi-square test for homogeneity, which is actually like pretty much 95% the same as this, except it's just in a different context. So I want to kind of go through that quickly, and then we'll be done with chi-square today. All right, and at least for the lesson is concerned. All right, so if there are no questions, I'm gonna move on. Okay, so chi-square test for homogeneity. The idea that behind this test is that is the distribution of a categorical random variable the same across multiple populations? So back to this example, it turns out that this can also be used for homogeneity because if I have different populations, in this case, the populations of hotel visitors, they could be categorized as female or male, let's say, and if I treat female and male hotel guests as different populations, my goal for homogeneity is that I have another categorical random variable where I want to see is this distributed in the females the same as how it's distributed in the males. All right, so this is very similar to independence, but again, when we say that in this case, one of the categorical variables has to be a different population, all right? Whereas independence, they don't have to be different populations, such as like anger level and heart disease risk. None of those variables are populations, okay? So in that case, males and females, that could be like two separate populations. Now we want to see if another categorical random variable is distributed the same across both of those different levels, all right? So again, the idea here is that when we take this, is it distributed in the females and is it the same as when it's distributed among the males? Okay, so is the red distribution the same as the blue distribution across those multiple populations? All right? So, same thing right here, homogeneity. By definition, and this is just from dictionary.com, homogeneity just means the quality of being the same or being uniform without irregularities, or it has the same properties. So in this case, we mean that the distribution is the same, all right, across all populations. This is the same example I had for independence at the beginning of those slides, but in other words, homogeneity means that the conditional distributions of one variable within the subpopulations are identical. All right. So when you look at that segmented bar graph, is the distribution of blood pressure, is it the same across all age groups in the study? Okay. And again, looking at the visual helps us get an idea of what that might look like, although we can obviously quantify this or be a little bit more scientific and conduct our chi-square test. Okay, so the hypotheses for homogeneity, under the null, we're going to assume that the distribution of a categorical variable is the same across all populations. The alternative is that the distribution of the categorical variable is different in at least one population. So if we're going to say homogeneity, that it has to be uniform across all populations, if at least one of them has a different distribution with respect to that categorical variable, that's enough evidence to suggest that the null is not true. All right? Okay, so everything below that is just another way of writing it or another way of saying it. You guys can read that on your own, but those are the hypotheses, you know, as concisely as you can put them, okay? All right. Okay, so moving on, unless there's questions, no? Okay, because we only have less than 20 minutes now. All right, so the observed data, one of the categorical variables has to assume the responsibility as the population. So I said that that was x. So notice that originally right here was x1, x2, xi, all the way to xr. Notice now I replace it with population 1, population 2. So one of our categorical random variables has to be the different populations. And then we want to say that the other categorical variable, that's not the populations, whatever it wants to be, that is distributed in each of these populations, and by homogeneity, that they're distributed the same way. So notice that each population has a little bit of a rainbow, okay, to them. And we want to say that this population in the first row is the same in the second row, and is the same in the ith row, and the same as the last row. So that's what we're trying to test in this case, okay? And again, notice that we're still summarizing in a two-way table because of two categorical variables, okay? All right. So going back to why we're doing this, we have a test statistic where it's observed minus expected. So the observed values are just the data, but now it's our goal to figure out, or our job, to figure out what are those expected values, okay? And we are going to run into a slightly different problem because, well, first off, expected counts, again, with every observed count, we should have an expected count. But the problem now is that before, when we got to this step and we said, oh, the expected counts in the table are just a multinomial expectation. But if you guys remember from independence, we represented this probability as an intersection and used the assumption of independence to split those probabilities as a product. But now in this scenario, we don't have independence to assume from the beginning. So now the whole story that I was telling you guys about how to find expected values for independence, that's not the same narrative as right now. Because my null hypothesis now is that the distribution of that variable y is the same across all of those populations. So is the formula the same or is it different under these assumptions? Okay, we don't know because we have to figure it out operating under what do the expected values look like under homogeneity. All right, so this one is a little bit more messier to work with. But here's a proposition, all right? So one proposition is that if I wanted to find the probability of being in this cell right here, this is the ijth cell, then the probability that's attached to this, which is right here, pi, j naught, okay? This could be approximated by the conditional probability being in the ith row. What's the probability of being in the jth level? So if I isolate the one population, the population that x is equal to I being in this population, what is the probability of being in this cell? Well, based on conditional probability, what's the probability of being in the intersection between the jth level and this population? That's just this guy right here, which is the expected value, I comma j, divided by the probability of the condition, which is the population I, which, again, taking the expected counts, that's just a ratio to however many observations fall into this population. This is just an estimate of what probability it is to be in this cell. Just take this, the counts in this cell, take it as a ratio to the sum in this population, because that's our condition. All right? So notice again the color codes, that's where I'm getting those values. Okay? But this is not the whole story, because if I'm trying to find expected counts, my formula right here, or my estimate right here, has what I'm trying to find. I want to find expected counts, but how can I use something that's unknown to me, or what I'm trying to find in this formula? So we're not all the way there yet. Okay? So that's just an idea, a proposal that in order for us to estimate the probability of being in this one cell right here, or the distribution of yj in this population, I'm just going to take the observed values in this level, in this population, and divide it by the total number of things in that population. That's basically what I'm saying. And then, again, that's not enough for us to figure out what the expected values is going to be. So, going back to our assumption under the null hypothesis, notice that under homogeneity, we have to say that across all the levels of, of the first level of y, in all populations, they have to be the same. In the second level, they have to be the same across all populations. So notice that, again, I color-coded it. So all the red levels, okay, this is the first column, column 1, they have to be all the same. So if you look over here, where is it? Like this one right here, how this first level of y is distributed across all these populations, these values have to all be the same. The second level has to be all the same. Same, same. Okay? So that's what under homogeneity, that's what I'm writing right here. Okay? Now, I just figured out this guy. The probability of being in the ijth cell. This is, we use the estimate that I proposed in the previous slide. That's the p hat I comma j. Okay? But for any ith or ijth element, it doesn't have to be this one. Obviously, it could be any of the other probabilities. Notice that in this one right here, whatever this cell or this probability is, it has to be equal to what everything else is equal to. So in this case, this is the probability right here. I know it's really hard to see, but these are more bolded than these ones. But whatever the value of all the green ones are supposed to be equal to under homogeneity, I'm going to say that it's supposed to be equal to some fixed value, which is p comma j. Okay? So now my goal is, if I found the estimate of the ijth probability, and it's supposed to be equal to that value that all the values are supposed to be equal to, well, what is this probability going to be? Okay? So, in this case, the question that we have to ask ourselves is, under the null, how are the levels of the categorical variable distributed across all populations? That is, what are the probabilities of all the p comma j's? So p comma 1, p comma 2, p comma j, p comma c. So this is what is the proportion of all the proportions in red? What is the proportion of the orange? Proportion of the green? Proportion of the blue? So these are just the proportions of how the variable is distributed across all populations. So if I find what that value is, p comma j, that's just the generalized probability for any of the rows or any of the columns I choose, then I need to work with that. So what is p comma j not? Well, another proposition. All right? So under homogeneity, for the jth level of the categorical variable, I want to find what is that p comma j, but again, in the population, I may not know what that is, so I'm going to use an estimate. So notice that this is p hat comma j, and I put a c right there to distinguish it from the other. But notice that this sample estimate is equal to, and you can look at it at the table, if I want to find what all the green values or the green proportions are equal to, what a good estimate for that is I'm going to add up all the observations in the jth level. So O1 comma j, O2 comma j, all the way to OR comma j, and I'm going to divide it by the total population right here, which is the row sum in this population, the row sum in that population, so on and so forth. And then when I add up all the O's in green, well, isn't that just the column sum of the jth column, which is right there? And then when I add up all the row sums, that's just going to give me n. So it's just this ratio right here. Okay, all the elements in the jth level divided by the total. So that's this p hats comma j. Of course, all the individual p hats in each of the populations, there should be unbiased, but I'm combining all of them because combined, if they're estimating the same proportion, because they should all be uniformly the same, then the combined should be more accurate. Now, do you guys remember where this is from or where we've seen this?
Unit 4.
Unit 4?
I mean, it's like some Unit 5, right?
Unit 5? You guys even know what Unit 4 and Unit 5 were?
Unit 4 is probability. Unit 5 is segment distribution.
Okay? No. It's actually Unit 6. What does that look like to you guys?
No.
Yes. Okay? What does it look? Okay, so we're running out of time. Alright, so it should remind you of the pooled proportion. If you guys remember from Unit 6, what the pooled proportion was. When we did a two-sample z-test for the difference in proportions, where our null hypothesis was that P1 was equal to P2, then because P hat 1 and P hat 2 are estimating the same value, taking the pooled proportion where you combine the sample proportions as one combined sample is a better estimate than the P hat 1 and P hat 2 that we had individually. So now, if under the null hypothesis, if I'm going to say that all of these p's should be the same value and they're equal to this singular value right here, well, an estimate of this singular value is just taking all the estimates for each of these individual ones from their respective populations and just combining it into one pooled proportion. That's where we get this guy right here, and the logic is the same as the pooled proportion when we only had two proportions. Now we're just generalizing it across multiple populations. Okay? Because if I were to eliminate those right there, the expected or observed value of the first population, of the second population, and the sums of those two samples, then that's literally the same as that. But I'm just extending it to multiple populations because that's what I'm working with. Okay? So, that's the proposition that I'm saying, is that whatever all those individual p hats in each of those populations are supposed to be under homogeneity, we could use the pooled proportion as a better estimate of that. And now, to find the expected count, I'm going to combine those two propositions. If I'm going to say that the p hat I comma j from now just that one cell, okay, is equal to that combined, okay, pooled proportion, and they're supposed to be equal in value in the long run, then what these individual p hats are equal to I set them equal to each other, and because I want to find the expected value or expected counts in the ij itself, I move this row sum over to the other side by multiplying, and I get this formula, which is exactly the same as it was under independence. But notice that I was able to get the same formula for expected value under different conditions or different assumptions. Okay, again, a lot of details, and again, a lot of you guys probably don't care, but it's very important to understand what you're doing with all of this. Okay, like when you do say, I have a null hypothesis, well, what are the implications of that? Okay, so again, that affects how you get your expected values, but turns out that the expected values for homogeneity are the same as the expected counts for independence, luckily for us. So again, to calculate the expected values, if you want the expected value in this ij itself, take the row sum of the ith row, take the column sum of the jth column, multiply those together as you see right there, and divide by n, which is the same as independence. Okay? So, once you find the expected counts, as before, compute the chi-square test statistic. Compute a p-value, compare against alpha, make a decision, and there you go. You have your chi-square test for homogeneity. All right, where again, it's virtually the same, except the hypotheses are going to be different because the hypotheses for homogeneity are different from independence. You still have the same conditions with the exception of now you have to check independence because that's not what you're assuming under the null, unlike chi-square test for independence. The calculations are the same. Interpretation is the same. So just like first block, I was not able to get to the example, but 95% of the problem is the same. The only difference between this and independence is that the hypotheses are different and you had to check independence here, whereas you didn't have to check it before. That's the only difference, okay? So with that, your homework is going to be published now, but you have 4 problems because I kind of had to modify because I didn't post the homework on Friday. So you do have homework tomorrow. I plan on going through inference for regression. So hopefully if I could finish that all tomorrow, we'll be done with AP Stats tomorrow. So hopefully that's, it pans out exactly how I expect it to. And with that, you only have 1 lesson after this, okay? So in any case, your homework is published. Try your best to do it. You might have a little bit of difficulty